Partial fraction expansion. We're going to find this technique useful when we have a function that's in the Laplace frequency domain and we are interested in taking the inverse Laplace transform of it, but we see that the right-hand side does not directly appear on our Laplace transform table. So sometimes the algebraic technique we can use to get it to look like something on the Laplace transform table is to do the partial fraction expansion, turn it into multiple fractions, and then maybe each of those itself does appear on the Laplace transform table. So what's the usual procedure we're going to take? I'm going to say there are different ways to do partial fraction expansion. This is not the only technique, but this is the way I'm going to present it in the following example and the way that I typically am going to be doing it. So first, we cannot always apply a partial fraction expansion. It's going to depend on what the denominator of the fraction we want to try to expand looks like. So one, it has to be factorable. So there's very specific times that we're going to see that the denominator of our fraction actually is factorable. Now in the example we looked at, it's designed so that it is going to be factorable and then we can factor it. But that's not always going to be the case. If we have roots of the denominator or poles of the function that are imaginary, well then we can't do a partial fraction expansion. There's going to have to be a different technique that we need to do. So if it is factorable, if we can find integer factors of it, then we want to do that and express our quadratic or maybe our third order fraction as this in this factored form. Then what we're going to do is write a fraction for each of those terms in the denominator, and we're going to equate it to our original function. Again, in the example, we'll see what this looks like, but we're going to have these unknown numerators that we're going to try to find. So then typically how I'm going to solve it is once we have this new right-hand side where it's this sum of partial fractions with these unknown numerators, we're going to multiply the whole thing by the denominator of the original fraction that we have on the left-hand side. And what we're going to be left with then is one equation that has our unknown coefficients in it. And what we're going to see is that we can split up that one equation into multiple equations because we're going to have terms that have just constants. We'll have terms that are attached to an s, we'll have terms attached to an s squared, and so on, depending on the order of that original denominator. And we're actually going to be able to split it into multiple equations based on those coefficients that we're going to be able to solve for the a, the b, the c, whatever the coefficients were that we split our partial fraction into.